All right. Hi, everyone. Thank you for coming to the Fishbowl Teleseminar. Our speaker today is Professor Gil Zussman from Columbia University. Gil received his Ph.D. at Technion in Israel. He was a postdoc at MIT, after which he went to Columbia. Gil has been very successful in research in wireless networks in particular, and he's received five outstanding paper awards, loads of awards of other kinds, as well as more recently, he's got a Vodafone Foundation Wireless Innovation Project, and I think he's going to tell us more about that. Please welcome Professor Gil Zussman.
Thank you for the invitation, and thanks for the introduction, and I'm glad to be in Texas remotely. So I'm going to talk about energy harvesting active network tags. Basically, I'll talk about measurements, algorithms, and prototyping. And before I start, I have to say this is joint work with several people here at Columbia University, several people in the group of Peter Kinget and the group of John Kymissis on the electrical engineering side, and several people in the groups of Dan Rubenstein and Luca Carloni on the computer science side. And in addition, within my group, several students contributed to that. The ones listed here are Ph.D. students, visiting Ph.D. students, or postdocs that worked on the project along the years. So what we are trying to develop, we call it EnHANT, Energy Harvesting Active Network Tags. These are small and flexible devices that can be attached to almost anything. You can see the form factor over here. Basically, they should harvest their own energy from light using a flexible solar cell and form a wireless network, exchange their IDs. Basically, we don't see videos transmitted over that, but the device's IDs, maybe the IDs of their neighbors, something about their location, and so on. Eventually, they would be able to communicate with other EnHANT-friendly devices, phones, laptops, whatever you want, and would support various tracking applications. So you could view it as one of the possible infrastructures for what's called nowadays the Internet of Things. So one representative application that we've been trying to prototype is to be able to locate a misplaced book in a library. So if you think about it, if you take a book from math and put it in physics or literature or whatever, the book is lost forever. So the idea here is to try to put EnHANTs on the outside cover of the book. The books will harvest light energy and will send their IDs to their neighbors in very short range. So we all know that the location of the book in the library is related to its ID. So if you place a book in the wrong location, the book and the neighbors will figure that out. Then they can forward the information to some infrastructure. It will get to the librarian, and he or she will come to the shelf with some device, could be their phone, blast the books with energy, and the book that does not fit in will turn on an LED and say, I'm here. So, of course, this is not a billion-dollar application. Libraries are disappearing. There are many issues. But you could think about many other tracking applications that could benefit from this type of infrastructure. It could be the boxes inside a FedEx truck, shirts in a Gap store, whatever you want. So basically, we started with this vision back in Mobicom 2009, and we've been trying to get slowly towards that vision. So, of course, we are not alone in the world. There are many other technologies and ideas out there. So just to put things into context, there are RFIDs and sensor networks, and I would say these are the nearest neighbors. So the difference between EnHANT and RFIDs is that RFIDs are a single hop type of technology. They are not self-powered. You blast them with energy and they reply. We envision a device that has its own source of energy, therefore can create networks with its neighbors. So that's the difference between RFID and EnHANT. On the other side, we all know there has been a lot of work on sensor networks. EnHANT will not have the type of, and I'll talk about the energy sources in a moment, but will not have the type of energy you even have in a sensor network, and therefore we don't envision the type of sensing, computation, and many other things that could be done in the sensor network. At the end of the day, this is a set of tags that are RFID replacements and can be connected to each other and form large-scale networks. So that's where we are. Now, if you look outside in the outside world, commercial devices cannot do this, and there are several reasons. If you go down to the physical layer, the solar cells that are designed for indoor energy harvesting still do not exist, or the right solar cells for indoor energy harvesting with the flexible form factor and so on still do not exist. The energy consumption of technologies such as Zigbee, Bluetooth, low power, and so on is still too high to operate with indoor energy harvesting. So just to put things into context, indoor you have 1,000th of the amount of energy that you could harvest outdoor. So you need really low power in order to be able to send your data around. And currently, at least, the network protocols are not energy harvesting aware, although there are many efforts to develop energy harvesting aware protocols in different communities. Now, I should say the commercial devices cannot do this, but they cannot do this yet. There are many efforts out there. Texas Instruments is developing devices that harvest solar energy. There are transmission or devices that are supposed to transmit some kind of energy to their neighbors. There are devices that are supposed to track the level of the battery, the solar cell, and so on. So there are many commercial attempts to develop different parts of the system, and we should be aware of that. So the EnHANTs project, as I said, it's a collaboration of several people, and we've been doing several things. So the first one, which I'll discuss, is characterizing the energy availability. What amounts of energy could you harvest? How does it behave? What are the dynamics? All of that is one component. Another part is developing hardware components. I'm not developing hardware components, but my collaborators have been developing UWB transceivers, organic solar cells. There was an attempt to develop a flexible battery, various components that could go into such a device, and we can test some of our algorithms using those components. The next step is developing energy harvesting adaptive communications and networking algorithms, of course. And finally, we are working on developing prototypes and a testbed of those prototypes that will use the components and on which we could evaluate some of the algorithms. So most of the talk is focused actually on the enhanced energy availability and the prototype, testbed, algorithm evaluation, but I'll say, of course, a few words in the middle about the types of algorithms that you need for these type of devices and what is the design space. So I'll start with the energy characterization. Basically, if you want to install a wind farm or a set of solar panels, there is a lot of data out there about how much energy you could harvest any point in Earth, more or less, and any time of the day, year, and so on. These are just two examples of maps that are available about solar and wind power. However, if you move to commonplace environments, let's say indoor, office, apartments, and so on, this is much less explored. We are talking both about indoor light and also object and human motion. So our first attempt was to try to understand how much indoor light can we harvest, or how much energy can we harvest from indoor light. Is this even feasible? And if it is feasible, what can we do with that? So people have looked at indoor light in the context of sensor networking, but most of the measurements were measurements of flux. Basically, how convenient is the light for you? This is more for ergonomics, architecture, and so on. There was no data for how much energy, and there were no traces of how much energy can I harvest in an indoor environment. So what we did an energy measurement campaign. We claim it's the first of its kind. We deployed sensors in different buildings around Columbia University, and we collected traces. Some of the traces were collected for over a year and a half. And we also had mobile measurements. So for the static traces, you could see here an example. These are 4 consecutive days in a graduate student office. You can see that they show up in the office, which is nice. But besides that, you can see more or less, how the energy behaves. You can see that you could predict somewhat the future, but there is variability between the days, which might depend on the fact that they opened the window or did not open the window, the weather was different, and so on. But you start to get a sense of how much energy, or what is your daily energy budget, and how does it behave.
Question here, Gil.
So I'm just curious, is this light from outside through windows, or is this light coming from overhead lights, or?
So mostly, we have all types. So we had measurements on the window sill where you saw the light at some point in the day. I believe this trace, for example, where you see the burst, is when the sun is more or less shining into the window. And we have measurements, on a shelf which is really away from the window. And we have in a lab that doesn't have windows at all. If you think about it, light properly, we are very familiar with radio waves, but at the end of the day, it's an electromagnetic wave. So as far as you go away from the window, there is a strong attenuation of the amount of energy that you can get from the outdoor environment, but you get something from your, indoor light. So we have, traces, and each trace, basically, where it was collected. Some of them were close to the window, some of them are outside. And I'll get in a moment to, what is your energy budget when you are in a dimly lit environment, or when you have some access to outdoor light, or when you are really outdoors. So I'll get.
So how far is it? I guess if you're going to go into this, feel free to tell me to wait on this. But how far is it? I mean, obviously, I know how much light these things put out. I should be able to calculate what percentage of that light is going to land on the particular space. How far do you end up from that?
So again, maybe how far I end up from what? Sorry?
From this sort of theoretical upper bound that's based on just how much light's being put out by the lights above me, the literal fixtures above me, and what fraction of the area that light's covering is covered by the sensor. Okay,
so again, let me make half a slide progress, and then I can answer that, because we looked at the efficiency and or the solar and so on. So if I don't answer it in 2 slides, then please remind me.
Okay.
So just before I move on to the real observations, I just want to say that we had static measurements, and I'll talk about them a little bit more in a moment. We also had mobile measurements. So for example, we sent a student to walk around Times Square at night, and even there, if you look at the levels of irradiance that you can get, around 50 microwatts per square centimeter. So if you start doing the math, you see that even at Times Square at night, you can harvest enough in order to send a few bits around, a few bits per second in every time slot. So that's some observations that we have. And one thing I should say is that the traces, we've been using the traces as input to simulators, because it's much more representative than to come up with some random process that theoretically represents the light that you could get. And we use them in the experiments, and I'll get to that in a moment. And other people, we place them online in Crodad and in our website, and other people have been using them in other simulations. So I think now I can answer some of the questions about, okay, what did we learn from that? So collecting these traces is important for both system design and algorithm design. If you think about system design, basically, you want to decide of how big would your battery be, how big is my solar cell, what should be my energy budget for transmitting. And if you start thinking about algorithm design, is how repeatable is the pattern, how can I plan for the future, and so on. So if you could make various assumptions, but just in order to get the sense, you have a 10 square centimeter solar cell, which is a relatively reasonable assumption. We assume a 1% efficiency for organic solar cell, which is a very conservative assumption, but again, we want to get a sense of how much we can get. So 1% of what falls on your solar cell, eventually you harvest. And we assume a 1 nanojoule per bit energy spending, which corresponds to our UWB transceiver. I'll talk about it later on, but it's not only our UWB transceiver. There are many efforts in UWB in different locations, and these are more or less. So when you take these numbers and you ask yourself, okay, how much could I harvest? So if you go to offices with little to no outdoor light, you get about 1.3 joule per square centimeter per day. And when you put in all the efficiencies and you assume that you want to operate in a continuous manner, meaning that even when people are gone, you want your device to be able to send something, eventually this translates to 1.5 kilobits per second. So of course, 1.5 kilobits per second.
A quick question.
Yeah, sure.
Is this 1.5 kilobits per second compute or data transfer? Because when you get into the transfer of the data, antennas, LNAs, all kinds of stuff eats your power budget big time,
Yeah, so this is the 1 nanojoule per bit is for, I would say, realistic transceiver with antenna and everything. So that's already there. But of course, there are many other overheads that you could imagine in the MAC and the physical layer, the headers and whatever, and coordination with your neighbors and how do you do sleep-wake and so on. But the 1 nanojoule per bit comes from the people that design the chip and have the transceiver working already. So that's if this answers your question.
Okay.
Okay. So, but again, of course, we have the raw numbers, and you could make, whatever assumptions you want. We think these are more or less realistic assumptions. Of course, if somebody comes up with a better solar cell, you immediately multiply, the efficiency goes from 1% to 2%, you immediately multiply your data rate. And if you move from organic solar cell, which we would like to use because it's flexible and it's cheap and so on, to amorphous silicon solar cell, the efficiency will be much higher. Again, the data rate will be higher. But this gives you some sense of what data rates you could talk about. That's the reason for these numbers. And again, you can see the numbers here. If you move to better or brighter offices where you have a lot of outdoor light, the numbers are higher. And of course, if you go to outdoor environments, just download the data set from the Department of Energy, the data rates are theoretically very high, but then there is no reason to use a very low power UWB transceiver. You could move to ZigBee or something like that and operate over their desk. But this is just to give you a sense of the difference between the indoor light and the outdoor light. As you can see, there's a huge difference. A few other things that we can see beyond the numbers are we have many energy profiles. So if you look at the graph down here, it basically shows you the same location over and over again, day after day. And you see that there is some variability between the days, but you could also assume that the sun or the light will show up more or less at the same time and so on. So you could use this if you want to start predicting the future or trying to do intelligent things. And predicting the future, we are not the only one playing in this field. So people have been looking at the correlation with the weather, the work week patterns. There is less light because people don't show up on Saturday and Sunday, and so on. And other things that we have done, there are correlations between different locations. Can I assume that different nodes in my office see more or less the same amount of light? Can they use this information in order to wake up at certain times and so on? And if you want to be very specific towards the solar cell, you could characterize the spectrum. Different solar cells have different efficiencies in different parts of the spectrum. So if you are using indoor light or if you are outdoor or different type of indoor light, then you might want to use different type of solar cells for your harvester. So this is the high-level picture in I would say, the solar energy harvesting. Just again, put things into context. If you talk about 1 joule per day, which is more or less your power budget, if you transfer it to microwatts, you talk about 12 microwatts. This is your energy budget. You have to run your microprocessor, you have to run your transceiver, you have to run everything using those 12 microwatts, which gives you a sense of how limited is that. And now, if you look at what we have out there, so these are, for example, batteries that are used by Mica 2 modes, other modes out there, and these are AAA or AA batteries. If you consume 1 joule per day, theoretically, out of those batteries, you could live for 18 years or 40 years. Of course, the battery will die much earlier, but this gives you a sense of how many joules are stored there compared to where we stand when we start harvesting indoor light. Similarly, a coin cell battery can operate almost for a year if you would be discharging it at a rate of 1 joule per day. So that's from I would say, the solar energy side or the light energy side. The other side is the motion energy. So you move around. Theoretically, when you move around, you could harvest energy. And there is a lot of discussion of wearable computing and other things. So the question that we ask ourselves is how much energy could be harvested by kinetic energy harvesters. Now, basically, you have some motion. The motion goes into the harvester generates power. We wanted to have a broader picture, and therefore we use the harvester model, in which basically you model the harvester as I don't want to go into that in too much detail, but some kind of a second-order mass spring, and basically based on the frequency of the harvester, how far, or I would say differently, the distance between the frequency of the harvester and the frequency of the motion will determine how much energy you could harvest. So if your frequency of motion is very close to the frequency of harvester, you will get a lot of energy. If it's very far away, or there is no frequent motion at all, you of course won't get much energy. So that's the idea here. And what we did, we basically collected or used acceleration traces. We fed them into the harvester model, and we try to understand how much power you would be able to harvest and how would this power behave. So the first thing we did, since there is a lot of discussion about the Internet of Things, we were wondering, how much things can harvest. So we shipped a box with FedEx, actually from Texas to New York. We checked in luggage with the device, the measurement device on a flight. We took it on trains. We took it on cars, various other things. At the end of the day, you could not harvest much out of this type of motion because it's not very periodic. So if you walk along, across the airport, during your walk throughout the airport, you harvest more than throughout the flight when the luggage is in storage. So this is something, again, to keep in mind where you talk about harvesting by things. And there are many other... Excuse me? Yeah.
Quick question. So how much better could it be? I assume then, like you say, there's one resonant frequency for this given harvester. One could imagine building a series of different harvesters and packaging it together into one package so that you can collect a lot of different frequencies. Basically, you can kind of harvest whatever the frequency happens to be.
Yeah.
How much benefit do you think that would provide?
So again, the problem with most of those things is that they are not very periodic. So you don't get too much, the frequencies are not, whatever you will do, you will not get close to them. Even if you try to say, okay, this was my trace, and now let's build the optimal harvester for a given trace, how much energy will I get out of, I don't know what, riding the subway? Right. But on the other hand, if you move to the next, I'll go back to the other one in a moment, but if you move to people, you definitely could use different, you can see here the motion frequency of different activities such as walking, cycling, going upstairs, going downstairs. You could theoretically benefit from having different or set of different harvesters for different frequencies or even for different people. You could say, okay, if somebody has an extra large shirt, he should have a different harvester embedded in it compared to somebody who has a small or extra small shirt, just because the frequency of motion is different, as I'll show in a moment, for these type of people. So definitely you could optimize the harvesters for people and for their activities, but again, if I go back to things, it's not very efficient. And the bottom line here is there is no, rocket science here. There are no big surprises, but I don't think anyone, because these are not the frequent motion, but I don't think anyone really tried to say, okay, how much would I get if I start reading a book? Will I get anything out of it? So we wanted to get a sense of where does this stand. Now, just to compare all those numbers that you have here, just walking gives you between and 280 microwatts. So all the activities, moving stuff, big deal. The only thing you could gain is if you start shaking things, then you get a lot. So if you run out of battery and you want to shake your device, then in a frequent motion, then you'll get a lot. Just before I move to the next slide, you disappeared from, okay, you came back. Okay, so going on with motion, so the human motion, again, you could, as I already jumped forward and said, from human motion, you could harvest energy. And to keep in mind, most of the previous work that started looking at it looked at a small number of participants walking on a treadmill and trying to understand what's going on. What we did, we took traces that were collected by somebody else. There was a 40-participant study, and they made people walk, run, cycle, and so on, and they measured acceleration, where their objective was to try to understand, can I identify the activity? If this is the acceleration, can I tell that the person was running or walking? Now, we don't care about what they were doing. Assuming that we know that they were running or walking, we were trying to understand how much energy could be collected there. And just to put, again, things into context, each color represents a different location of a harvester or an acceleration measurement device. And you could see the dominant frequency for walking, fast walking, running, cycling, and so on. And you can see how many microwatts you could harvest from each of those activities. So running gives you much more than walking, but walking still gives you something at the order of indoor light. So that's something good to know. And there are other variables here. Cycling, just because if you put the device on the leg, probably you'll get much more. But right now it's sitting in a location that is not really, doesn't have much impact.
Which location is which?
Yeah, excuse me?
Which location was which on the photo?
I think that's a good question. I was not ready to this question. Yeah, I have to look it up. But we have it online. I can send it later. Yeah, I don't remember which one is which. Yeah, so a few observations that are coming out of this is, for example, the exertion is not necessarily correlated to the power harvested. If you make an effort, it does not mean that you'll harvest more power. An easy example is that going downstairs gives you about 2 times more power than going upstairs. So making an effort doesn't get you power. And you could see here, for example, we just talked about the frequency. So the frequency is negatively correlated with the height and the weight of the participants. So theoretically, you could give them different harvesters for different pen size or shirt size or whatever. And we have other things that appear in the paper. For example, the power for the taller people is 20% more than the power harvested by the shorter people when they run. And there are these type of observations in there. So these were all very controlled activities. You know, you tell people go and run, and then you measure it. The other thing is that if somebody has his own daily routine, how much energy can you get out of that, and how does the energy behave? So we had collected the traces for a small study. I have to admit it's not a huge study, but it's 5 participants, 25 days. Overall, we have more than 200 hours of acceleration information, something that I don't think is existing anywhere else. And basically, these people were carrying the device from the moment they left their apartment or the moment they woke up to the moment they went to sleep. So you can see here, for example, a 12-hour period. You could see the acceleration, and you could see how much energy was harvested during the day. The person was going to work, and was sitting near his desk, then got bored, went around, and ate lunch, didn't do much, and then started moving around again. So basically, when you start looking at these traces, the differences in energy availability is mostly related to the amount of walking. And we are in New York City, people walk quite a lot, but we had different type of people. And most of the people are stationary most of the time, so 95% of the energy ended up being collected during 5 to 7% of the day. Now, if you're just, again, interested in the bottom line is that if you take a daily routine of a person, you could support 1 to 2 kilobits per second of, again, transmission throughout the 24 hours, which is very similar to dim indoor light environment. And you could, of course, start thinking about, I can combine my harvester, it will harvest light and motion, and when the person walks outside in the evening, it doesn't harvest light, but it harvests motion, and when he sits in his office, it doesn't harvest motion, but you get light, so you could play with that, of course. So the traces, again, will be available online. And one observation that we noticed is that it's very clear that these are not IID or Markovian processes, so you could very easily show that they are not, but you could also show that the results, once you go into the algorithmic side, if you feed the algorithm an IID or a Markovian process, or if you feed it a real trace, you get results that are really different. So there are many people out there writing papers about energy harvesting adaptive algorithms, and you have to keep in mind that most of those make assumptions that, at least for this type of harvesting, are not necessarily realistic. I think they'll be very happy if we come up with a trace that shows that things are IID, but it's the situation right now. So again, this was a quick overview, but the paper will be in Sigmetrics, so that's that. So basically, up to now, it's how much energy can I get. Now, of course, I need this energy in order to do something, and the next step is the resource allocation algorithms. So the difference between this environment and other environments is, first of all, of course, you have dynamic energy availability. It's not just you have your battery level and the battery goes down. So energy, some nodes have energy, some nodes have light shining on them, some don't, and so on. Now, the other thing that is very different from sensor networks, in sensor networks, you start in some battery level and you try to maximize your lifetime until your node dies or the battery is depleted. Here you start somewhere, you go down, then you go up, then you go down, you go up, you go down. Theoretically, you want to be able to live forever. So this is something to keep in mind. And the last thing that we have observed is that you could support very limited control information. So theoretically, you want to come up with very sophisticated algorithms, run some MATLAB in every node, and exchange a lot of information. But at the end of the day, if you are able to support 1 or 2 kilobits per second, if you start sending too many control messages, basically your channel is just wasted for the control messages. So this is something to keep in mind. So, yeah, question? Okay. So I won't go into too many algorithms, but I do want to give an overview of the design space, because there are many things that can be considered once you start designing algorithms for this domain. So first of all, the ratio between energy harvested and the energy storage capacity is basically huge, because as I said before, the ratio between indoor light and outdoor light is almost 1,000, or more accurately, 800 times different between the amount of light you could harvest or energy you could harvest outdoors and the amount of energy you could harvest indoors. So of course, if you operate in a outdoor environment, you are less sensitive to many things. On the other side, the batteries that are being used, for example, in sensor networks are 5,000 times larger than batteries that are now developed for energy harvesting devices. So again, if your capacity is very limited, you have to be very careful in order not to overcharge it and so on. As anything in networking, you can design algorithms for nodes, for a link, for a cluster, for a network, and things becomes more and more complicated as you try to scale them to the larger network. And the last thing I want to say here, and I'll get into details in a moment, is that the energy storage type can be different. So traditionally, you would use batteries. But since you're talking about very small amounts of energy, you can now start charging capacitors. And when you charge capacitors, you observe some nonlinear behavior that does not exist in batteries. And then when you plug this into your algorithms, it makes your life more difficult. So these were a few of the design considerations. The other are the environmental energy model. And for each of these models, there are many related works, so some of them are listed here. So the first model is the predictable energy profile. You see here, for example, 4 consecutive days outdoors in Las Vegas, and the amount of irradiance or the amount of energy you could harvest in each of those days. So there are many unpredictable things in Las Vegas, but the energy that you could harvest is very predictable. So this is something you could design your algorithms to such an environment. Another environment, and again, people wrote papers about this, it's partial predictable energy profile, partially predictable. You know that there will be light tomorrow, you know that more or less the amount of light that will be there, but you don't know exactly how it will behave. So you could think about algorithms for that environment. You could have a stochastic process, which is very easy to represent. You just say, okay, I know the distribution, and I will tailor my algorithm to that. You could maybe try to fit a stochastic process to the student walking outside in Times Square, and there are many people, mostly inspired by the back pressure type of algorithms, that are using stochastic processes in order to model the incoming energy into the battery. And of course, in reality, in many cases, you cannot really fit a model to all of that. I just talked about the kinetic energy harvesting. It's not very easy to fit a model to the amount of energy that you harvest through your day. So these are all the design considerations, just to keep in mind what is our objective when we design algorithms. So we know that the energy sources are highly dynamic. Our objective, since we assume that we have a backlog of messages, we want to send our IDs around, we are boxes inside a FedEx truck, and we want to exchange messages, and we want to be able to exchange messages all the time, more or less, as much as possible. So we want consistent operation throughout the day or whatever our time slot is, and unrelated to the arrival of energy. So ideally, if this would be my energy profile, I would like to have energy spending rate as the blue line, just spend the same all the time. Clearly, if I have a limited energy storage and I have other constraints and so on, some cases I won't be able to support that, and I'll have to spend more when the light shines on my device. But that's the objective. If you think about this objective, basically this objective tells you that you want to require fairness not only between the nodes, but also between the time slots. That's, I think, the easiest way to think about it. You have several time slots, and you want fairness between the time slots. Of course, you also want fairness between the nodes because you want to be able to collect the information from all parts of the network. So that's that. Now, fairness could be treated in different ways. One is the utility maximization framework, I assume most of us are familiar with. We want to maximize the sum of the utility, and the utility can be some concave non-decreasing function. Other tools that we can use is lexicographic maximization or max-min fairness. Basically, we want max-min fairness. There was a lot of work, of course, on max-min fairness, but here it's not just max-min fairness between the nodes, it's also max-min fairness between the different time slots. Now, the last component here is the energy storage device. So, as I said before, the energy storage device could be either a battery or a capacitor. We have discrete time, and in every time slot we have some battery level, we have the capacity, we have some charge level, we have the capacity, we have some energy arrival, and we have some energy departure or spending rate, which reminds us many things that we know about queues and queuing theory and so on. One more thing that we have here is the delta or the resolution. We cannot just spend whatever we want. We have to spend in some given resolution because we are using a real transceiver and so on. So if we look at the evolution of this device, basically it reminds us of a queue, and we can use several of the tools from that area. We want the level in the next time slot will be the minimum between the capacity, the current level, the arrival, and the departure. The interesting part is that when you move from a battery to a capacitor, things become more complicated. So, for example, in a battery, whatever your irradiance level, for a given irradiance level, whatever your energy storage level is, you would get a constant amount of power into your battery. So the power depends only on the irradiance level. So in the case of a linear energy storage device or a battery, the amount coming in is a function of whatever is shined on your device. In the case of a capacitor, whatever goes in is a function of your current energy storage level. So when the capacitor is in good shape, in the middle more or less, whatever you collect goes into storage. At the beginning, when it has the low storage level, it's very difficult to push stuff in, and towards the end, it again becomes very difficult to push stuff in. So if you look at it here, actually your dynamics now have a non-linear component inside. So we looked at various algorithms for various scenarios. I will not go over all of them. I'll just go over some examples. But we looked at the predictable energy profile. We looked at the node and the link. We have optimal approximation algorithms. And we looked at the stochastic case. And we have the case for when your energy inputs are stationary, which is very easy to assume but not necessarily realistic. Or when you talk about non-stationary inputs, let's say you have a device here, tomorrow it's there, and so on. It has to somehow learn where it is. And for the case where there is no model, we also have some results. We have some heuristics. We have online algorithms. And we have several heuristics for the case of a link in a network that were actually implemented in the testbed. So this is where they are. So I'll talk about just a couple of things. So in order to talk about the case of a single node Bursty energy arrival, which is, for example, the case of kinetic energy harvesting, and a capacitor, I have to extend the model a little bit. So why do we care? Why do we want to charge a capacitor and not a battery? Let's say you do kinetic energy harvesting. You have highly variable harvesting. You'll have many charge and discharge cycles. And as time goes by, if you use a battery, it will deteriorate, while the capacitor will survive. However, the capacitor has this feature or function or whatever you want to call it, which is non-linearity. Moreover, the capacitor has leakage, and it has some kind of an inefficiency. When you discharge it, you discharge more than what you need. So all of those things go into account, have to be taken into account, and they go into your energy storage evolution equation. So I'll go over a few of them. So we've seen this already. This was a simplistic model. Now, if you want to make it more realistic, you say, okay, if I have a capacitor in every time slot, I'll have a leakage. The leakage is a function of my charge rate. Moreover, the charge, as we've seen already, is a function of my current charge rate and, of course, the incoming energy. And how much I discharge, I have to decide how much I discharge, but I discharge actually more than what I need for my transceiver, and how much more is also a function of my charge rate. So all of those go into the energy storage evolution equation, The problem is, of course, NP hard, but what we did is we came with some kind of FPTAS online algorithms, and we tried to evaluate them using the traces that we collected. So I'll show just a couple of results. Basically, we have a few algorithms. We evaluated them using the trace that was collected, the kinetic energy harvesting trace. We divided it, in this example, to 66 consecutive 10-minute intervals, and we want to see how the different algorithms operate. So this is the FPTAS. Just to be happy, the FPTAS ratio to the optimal is relatively good. It's 98%. So you could say, okay, I get an approximation algorithm, but in reality, it performs quite well. If you want to look at how the algorithms compare to each other, so you have the FPTAS, and eventually you have some kind of a greedy algorithm that can operate online and react to whatever it sees. So you see here the rate that you could support between 0 and 2 kilobits per second as a function of the size of your capacitor. Okay, right now it's in microjoules just to make things convenient for us, but you have a size of capacitor and you have the rate. And basically you could see that the optimal algorithm up here, you could see the approximation algorithm up here, and you see the greedy algorithm down there. So up to some capacitor level, the greedy algorithm operates relatively well. At some level where you could be more, you could be theoretically smarter and keep something for the future and so on, then the greedy algorithm starts to deteriorate. And the last example that we have here is, again, the data rate as a function of the size of the storage device or the capacitor when you compare the algorithm for the case of a battery and for the case of a capacitor. And you can see that you gain something by operating a battery, at least on the algorithmic level, but you lose from the characteristics of the device. As I said before, in such a case, from the hardware point of view, it might be much easier to use a capacitor than to use a battery. So that's that. One more algorithmic result I want to mention, but just before moving to the testbed, is that we looked also at the case for predictable energy profile. I know exactly the future. This is, of course, a theoretical result. I never know exactly the future. And I want to forward in a multi-hop network. So if I want to operate in a multi-hop network, I have to make some assumptions. One of the assumptions is that I know the future. So here, this is a problem that has not been considered before. Max-min fairness over a network where you have energy harvesting devices and you want max-min fairness between the node and the time slot. Eventually, you want, you want the different nodes are given paths from source to destination, and you want to determine the rate of energy harvesting in the rate of energy spending in each node. The nodes are sending their own information and forwarding information by others. So basically, we have an algorithm. It operates well. But one thing to keep in mind is this is a centralized algorithm. This could be only a benchmark to some distributed algorithm that will really operate in such a network. So this was a very quick overview of the algorithmic side. The next step here is basically to say, okay, we want to evaluate those algorithms, and for that we came up with a testbed, and we work with these algorithms in the testbed. So as I said before, there is wide interest in small self-powered nodes, but they don't exist. And our vision is flexible tags that will be an infrastructure for the Internet of Things. So we designed the prototype. We designed a testbed which includes several prototypes, and we use this testbed in order to start evaluating some of those policies. So one thing I should say that and I'll go over it quickly in a few slides, there are many students involved in that, and we have a paper here actually in a computer science education conference talking about how did we get from point 0 to where we are now, working with undergraduate and master students and high school students and so on. So this shows you more or less where we were and where we are now. We started back in September 2009, and you can see a few steps along the way. Each of those was a demo in a conference. I think we started in SICON 2010, and our last demo was in InfoComm 2013. And basically, as time went by, we phased out some of the off-the-shelf devices and replaced them with custom devices. For example, initially we were using a mode and we were using the transceiver of the mode. Right now we are using a UWB radio that was designed in Colombia. Similarly, we were using some manual lights. Now we have automatic lights and so on. So you could see, if you're interested, you could take a look at the slide and see how things evolved. Now, if you are really interested, there is a video in YouTube that shows you all the test bed as it was in one of the phases. I'll just go very quickly over a part of the video. So the prototypes are basically, you could see here the form factor that we envisioned. This is a flexible battery that we already integrated with the prototype. This is a flexible solar cell that they integrated with the prototype. Of course, this thing is a mock-up, and the prototype right now looks like that. But you could get nowadays flexible batteries and flexible solar cells. Unfortunately, the company that made those flexible batteries went out of business. So right now we are back to non-flexible batteries. But the prototype has an energy harvesting module. The idea there is to use the solar cell in order to charge the battery, to report back to the control module how much energy is coming from the solar cell, what is the battery state, and so on, and also to be able to discharge the battery in a controlled way. It also has a UWB communication module. It communicates using a UWB transceiver that I'll talk about in a moment. And it is using basically a Mica-2 mode in order to control the device. So we are using a legacy Mica-2 mode running TinyOS, but we are not using it to transmit or to do anything wireless. We are just using the microprocessor because it's very efficient, I would say, to inherit many of the functionalities of TinyOS. So within that, we run energy adaptive data rate, topology control, flow control, and so on. So I'll say a few words about the transceiver. The transceiver was fabricated by the group of Peter Kinget here at Columbia University. Basically, it uses ultra-wideband impulse radio. So the idea of ultra-wideband is that you send very short pulses at the order of nanoseconds, and you can shut down your circuitry between the pulses. So this makes things very energy efficient, but you don't have a carrier wave. So if you look at the energy consumption, we talk about 280 picojoule per bit to transmit and 1.65 nanojoule per bit to receive. And these are the numbers by the group of Peter, but there are several other groups in Michigan, MIT, other places that more or less report similar numbers. So just to get a sense, this is compared to hundreds of nanojoules for Bluetooth low power or Zigbee. Now, the interesting thing from the networking point of view is that the energy to receive a bit is higher than the energy to transmit a bit. So we are used to think about the case in which transmission is the difficult thing, I'll receive it anyway. So here, actually receiving costs us more than transmitting, significantly more, if you can look at it, because you have to listen to those nanojoule pulses, and finding them costs you something. So we integrated this transceiver with the prototype. The challenge is that basically, so it consumes, just to be, it consumes half a gigabyte, but in a gigahertz, half a gigahertz, but in very, very low power. And the difficulty here is that because you don't have a carrier wave, you cannot do the traditional CSMA, or at least theoretically people claimed you cannot do CSMA using UWB impulse radio. However, we wanted to be able to at least compare CSMA to other things that are very simplistic, so we implemented something to listen to the channel for a very short period and determines if something is going on. But again, keep in mind that there is no carrier wave, so you have to listen for a relatively long amount of time, and this costs you something. So the question is, what is the trade-off from the energy point of view between doing something along the lines of CSMA and using something simple as ALOA? So we ran several experiments in the testbed. Most of the previous work, again, was very theoretical. For ALOA, you get some kind of textbook results. The interesting part is that for CSMA, despite the fact that you spend really relatively large amount of energy on trying to understand what is going on in the channel, the energy per packet for CSMA is still much lower than for ALOA. So right now we ended up with running CSMA, some kind of CSMA over UWB, and at least our claim is that nobody really sends multi-hop data over UWB transceiver beside us. So that's that. The other component that sits there is the energy harvesting module. As I said, it receives power from the solar cell, charges the battery, tracks the battery state, and the interesting thing is that we can discharge very controlled amount out of the battery. So if we want to emulate a transmission that costs more or costs less, we can discharge the battery in relation to whatever we want to decide, and this theoretically sounds very simple. Practically, it took us various generations of putting together this hardware until we got to that state where we can really test algorithms in the test bed. The last thing that, of course, I did not do, but the John Kymissis group made was the organic solar cells. So they fabricated several organic solar cells during the lifetime of this project. And from my point of view, why is it interesting? You could plug into your test bed either an organic solar cell or a regular amorphous silicon solar cell. And the interesting part comes here. If you look at the performance of these two types of solar cells, so this is the amorphous silicon solar cell. For different level of irradiance, how much power eventually goes into your device. And this is the organic solar cell. Now, this means that basically for different levels of irradiance, you don't get a linear function as the power goes into your device. And if you put two different traces onto your device, this is a day that I measured somewhere, the amorphous silicon will behave differently from the organic solar cell. Why am I latching to that? Because most of the simulation work just assumes that basically I measured how much light I have, I will get a linear function of it as energy, and we did very similar things at the beginning, but once you go into the test bed, you quickly observe that reality is quite different from that. So as I said, we have a test bed. The test bed has, each of these is a prototype, and the prototypes basically sit under lamps that can control the light. They communicate back to a PC, and they tell you what's going on. And I think the best way to show that is using, I have a very short video, so I'll see if it goes over WebEx, but I'll at least try. So do you see changes?
Yeah.
Okay.
Not bad, actually.
This is the test bed. You can see here the control and monitoring system. You can see the different 4 different nodes in this case. They are connected via Ethernet back to a PC in order to tell it what's going on, but they communicate wirelessly. Every time a packet is sent, we see this LED blinking. So you see the whole thing, and the important components are this energy harvesting module, which is connected to a solar cell that was made here in Colombia, charges this battery, which we can play with, and this UWB transceiver that was also made in Colombia. If I go fast forward, I want to show the dynamic operation. You can see here, almost. Okay, we can see here Gerald turning on some lights. And as he turns on the light, you could see what's going on in the test bed. So you see 4 nodes. Each of the nodes, you could see the battery state, how much light it harvests, and also, of course, you can see it in the graph. So here you can see that the power went up. As the power harvested by this node, who is right now the coordinator, went up, it allows other nodes to transmit with higher data rate. Now, when he shuts down the lights, the node receives less power. This will impact eventually its battery, but very quickly it sends control messages to other nodes to reduce the transmission rate, and you can see that the transmission rate go down very quickly. Other things that you could see here is that they change the topology, they change the forwarder, and other things that happen dynamically. So this is, of course, a very short semi-demo, but it just gives you hopefully a sense of how things behave. So
2 questions there, right?
Sure.
So one is, are you saying that all these boards run on that 1 picojoule or whatever, 1 nanojoule that you're harvesting?
No, so the chip, eventually, the board has a lot of, I would say, debugging components and programming components and various other things. So if eventually we miniaturize it and make it into 1 chip, then the energy consumption is 1 nanojoule per bit. If you go to the circuits paper by Peter Kinget and others, that's the amount they report there. But the consumption that we have right now is huge. You need to in order to power the whole thing, you have like 16 power plugs running here. So I'm not saying that this is an energy harvesting system. This is a prototype of an energy harvesting system where the microprocessor consumes something and everything consumes something. So, but what is realistic here is that you do charge energy, using a solar cell into a battery. You discharge the battery in the amount that would be consumed by a real device, and you transmit using real UWB transceivers. But in order to make this into, I would call it a product, you should take it out of the university. You should not do it in a university environment. It would be much quicker. So
okay, then sounds good. The other question is, right, this is is the UWB impulse radio, like, for the same data rate, less energy consumption than, let's say, traditional modulating? I don't know if you happen to know this, I'm just curious.
So the question is that, first of all, we are using very, very low data rate just because that's what we could theoretically support using the energy, the energy harvested. So theoretically, this UWB transceiver can go up to 1 megabit per second if you want to, but we don't have the energy to support so many pulses per second. But for the low data rates that we are using, if we will now run ZigBee, or which we have actually running theoretically here because we still have the modes there, it will consume much more power than the UWB. And the key here is the distance between these pulses. You don't do much, while in the other technologies you transmit your carrier wave anyway. So that's the key. Now there are other challenges. How do you synchronize and so on? And because synchronization is not straightforward, the receiver actually consumes more than the transmitter. But overall, if you compare the cost per bit for these very low data rates, UWB will give you lower cost per bit right now.
By a lot, can you sort of, like, is it a big ratio between?
So I would at least say 10. Right now, if you compare UWB, again, I would say the UWB transceivers that are developed here in Michigan, MIT, and all those places, the claim made not only by our collaborators that the ratio is about 10 times between that and the lowest power ZigBee you could come up with, or something along those lines. So that's and again, these are several groups out there that are doing very similar things.
Thanks.
Okay, so you've seen the control and monitoring system. Basically, it reports back to the PC and allows us both to debug and to demonstrate the operation of the system. The other thing that we didn't see, because this is a relatively old video, is that by now we have a light control system. So the light control system, basically, we have these light boxes, and you could feed each solar cell with different amounts of light. You could have 3,000 different irradiance levels. You can change them very quickly. You could do it manually, which is nice, but the more important part is that you could feed a trace to it and tell it, okay, now go and fast forward the day that happened in my office in this solar cell, and fast forward the day that happened in the corridor in the nearby solar cell, and then you could test under this scenario a given algorithm. So it gives you the opportunity to test several different algorithms under exactly the same scenario, something you could not do if you take these nodes and put them outside or in the corridor or in the office, because you could never repeat the same scenario again. So that's that. And we claim that it operates very well. You could see here an example. These are 2 traces that were collected, and then we ran 26 repetitions of those traces and measured measured the difference between those repetitions and the differences that the device observed. And keep in mind, these are all real solar cell, real lights, real hardware measuring and everything. The differences are below 2.1% for all those repetitions. So at least we can feed the node with very repetitive traces. And this brings me to some of the evaluations that we did. Again, I'll go over very, very quickly over a couple of examples. So here are single node policies. You have a single node. There are many algorithms out there proposed since 2006, 2007, and on. Some of them are optimal algorithms. Some of them just say operate in constant rate. Others are very simplistic, say, okay, whatever you get, go and spend it, and so on. So we try to run these algorithms in our node, and we feed it with a trace, and then we run the optimal algorithm with some, if you look at the red and blue, this is with some capacity, and we have simulation results and we have experimental results. What's nice here is that the simulation results and the experimental results are very close to each other, and this actually makes people, both the experimental people and the simulation people, quite happy. And you can see similarly the evolution of the battery state and more or less the ratio between the optimal solution and some heuristics that were proposed in the past. Going forward, we have similar results. I won't go into too many details. I think I'm beyond my time. So we have similar results for a link between 2 nodes. How does this behave in simulations and in the testbed? when the nodes actually, each of them makes its own decision, and they somehow coordinate among themselves. The bottom line here is that you get very, very good results if you just let each of them make its own decision, and then they decide to transmit together. And this goes to a multi-hop network. You have a coordinator. The coordinator collects some information from the nodes regarding their battery state, regarding the energy harvested, and then allocates them some rates. The key observation here is not so much how much do you get, which is about between 0 to 3 kilobits per second, but the ratio between how much you get and how much control you send around.
So Gil, scheduling here is through CSMA, is it, in your multi-hop network?
So scheduling here is CSMA.
It's CSMA, okay.
This is CSMA over UWB.
Right.
Okay. But here it's more, I would say, looking at the allocation algorithms and how they behave. And what I want to say more about, less about the algorithm, but more about the control. You could let the controller send control information more often and tell you change this, change that, and so on. But as the control data rate goes up, your real data rate goes down linearly with that. So you can be very clever, but with the control information, you just kill your regular messages. So this is something to keep in mind. And the last observation we have here is basically a network with 4 nodes. You change the relay or the forwarder, whatever you want to call it, and there are many algorithms that we tested. We fed it again with different traces, and you could see more or less the ratio of the data rate that you get compared to the ratio of the best algorithm you could use. And the results here are not very intuitive. Some very simple heuristics operate better than cases in which you decide to change your operation based on the battery level and so on. So just to say that many people worked on that. This, we had more than a 150 semester-long project by more than 70 students that contributed to putting together the testbed, evaluating the algorithms and so on. So should give them some credit. And I'll skip this slide, but they're all very happy, and we had an educational paper about that. The future work, we want a bigger testbed to enable us to scale these algorithms. It's very, limited to test algorithms in a case of 4 nodes. We want to go to 30 and up to 30 to 60 nodes, and then to be able to control them more efficiently using Raspberry Pi on the backbone and so on. From the theoretical point of view, we want to keep working in the area. There is a lot of talk about the Internet of Things. We talk about the Internet of Tags. So how those tags operate from the real physical layer, real hardware, up to the application layer, there are many questions there. So to conclude, we looked at the properties of environmental energy sources. We have algorithms that adapt to environmental energy availability, and we designed the components that eventually went into the prototype and now work in a testbed. One bottom line here is that I started this from the more theoretical point of view. So in theory, practice is simple. In practice, theory is much simpler. So that's a recommendation to you. And again, as I said, this is a collaboration of several people, all listed here. Thank you.